Thank you for introducing Jürgen. It's a pleasure to be here in the webinar, and my talk is about preservation of grain by grain cooling with Granny Frigor. Protecting the quality of grain is our concern, as grain can only be harvested once a year but must be available throughout the year for the processing to produce any kind of food product or feed. Therefore, we must store the grain in silos mainly, and we must manage it to keep the quality and quantity to maximize our profit out of it. The grain cooling process, here shown in this graphic, is simply described. The Granny Frigor sucks ambient air through a dust filter to clean it, as the dust may accumulate in the unit, which cannot be accepted as it's reducing the efficiency. Then this air is blown into a cooling chamber. There we lower the temperature wherein the dew point will be hit. We get condensed water, which will be drained out of the unit. Then this air is conveyed into a chamber where we now lower the relative humidity of the air, as high humid air cannot go into grain, as it will spoil the grain by moistening it. So we adjust the relative humidity by the heating register or by the hygromat unit. Then the air, cooled and dehydrated, is brought into the plenum chamber of the silo. From there, it now enters the grain. It passes through the grain, absorbing the heat of the grain, lowering its temperature. The cooling zone will smoothly rise from the lower end of the bulk and rise to the upper end, where then the air is exhausting out of the silo through the vents. As we see, the air is not only absorbing the heat, but also has a potential to absorb some moisture. According to the physics of air, when air is made dry and warmed up, its relative humidity is further decreased, and thereby we can, according to the equilibrium moisture content, remove water from the grain. However, that is limited to the level of equilibrium moisture content, and if the grain is rather dry, nothing will happen. I show you this principle in a small animation. Here we see the Granny Frigor linked to a set of silos by a pipework. This pipework is now connected to the air entrance. The Granny Frigor is now bringing cold and dehydrated air into the air distribution system, and then this air will enter the grain, absorb the heat and the moisture until the silo has been cooled. Then the airflow is shifted to the second silo, and the same procedure is continued until the grain has also been cooled. We see that the installation of one Granny Frigor can suit several silos, and the operation is rather simple and can be controlled by the air dampers here in this example. However, it is also possible to move the unit from silo to silo, as it has wheels, so it's movable, and this makes the investment rather decent. We see here an example of a Granny Frigor linked to a flat bottom silo. The connection by the flexible hose is rather simple. The unit is secured against moving, and it's just plugged to the power grid. Then the unit could easily be connected to the silo on the other side by connecting it to the air entrance of the silo, as we see here, which is closed by the cover. Another application for the grain cooler could be applied to a silo cell system which has hoppers. Here we see the Granny Frigor also connected, as formerly seen in the animation, to a pipework. Each silo has a dumper where we guide the air into the air silo cell, and we cool the grain there as well. Here the practical example where we see the Granny Frigor connected by the pipe to each hopper. In this silo cells, here for example, a picture from a tropical country, is white rice stored. An alternative for the application could also be using bulk storage in warehouses. There we would implement an air distribution system where the Granifrigo is connected to the main canal, from where then half-round perforated metal sheet topped on the bottom of the floor are incorporated, and then the grain would be just bulked inside, and the Granifrigo could be using to cool the grain. Here the practical pictures. We see that the empty space is then set up with the pipeworks. The pipeworks are then covered by the grain, and the application can start. In managing grain, we feel that there are several concerns. Here you see the silo wall being covered by baked grain, which was, so said, glued to the silo wall as there was open water in combination with dust. This combination will lead to losses of grain. It is here only a decent loss. However, when things go worse, then we see that grain can bake to each other like a rock formation. Here, the grain cannot rather move out of the silo by gravity anymore. Now it's critical as somebody has to go inside to loosen the grain and to make it unloaded. That is, of course, life risky and must be taken under high security and safety alert. This nature of grain comes from its respiration activity. Respiration is the nature of any kind of living creature, and as we know, inside the grain, which is natural seed, is a small embryo which wants to stay alive, and therefore it has to generate energy. This energy is created by the respiration, which is conversion of carbohydrates by oxygen into carbon dioxide, water and heat. Of course, water and heat are dangerous for our storage condition, as it's very clear that water will create living condition for fungus or for insects. However, the heat is, so said, the escalator for the respiration activity, so that this will shoot higher and higher and will create more water and heat. In the mass balance, we see that out of 1 kilogram of carbohydrate, we generate almost 580 grams of water. That means we take out dry mass and add water to the silo. That would lead to a moisture increase of the grain, which naturally is not so often observed because there is a grain management application done called aeration, where ambient air is just put through the silo to dissipate the heat, and thereby it will also absorb excess moisture. However, it's very clear that we lose grain mass during this kind of respiration. The good news is that this respiration activity depends on moisture content of the grain as well on its temperature. This was already investigated in the 1960s of Mr. Jean, who gave us these results which are shown in this chart. This chart is showing the grain's temperature on the lower scale. Then we see colorful lines which symbolize lines of equal moisture contents of the grain, coming here from 13 up to 30. And we see that the result, the heat generation, is scaled in a logarithm scale. That means it doesn't go linear, it is going into 10 times for the same segments shown here. What is very clear is that with increasing grain temperature, the heat generation is increasing. And additionally, with more moisture content of the grain, the same heat generation will also increase, but much more. The given example here for a grain which is 30 degree warm and 14.5% moist indicates that we have a heat generation of 0.8 megajoule per ton per day. This is now not really clear for us what does that mean, because we cannot imagine what heat generation means. In this concern, I have translated this into something very realistic for us. I made an example for losses of corn. We see here the given data, corn as our type, the 14.5% moisture content, the 30 degrees centigrade. We put a monetary value for the grain price. We store this grain 4 months and we store a quantity of 10,000 metric ton. All this value go now in the grain loss formula, the heat generation from the former chart, the 0.8 megajoule per ton per day, the storage period of 120 days, the storage quantity of 10,000 tons. We divide this by the energy content of 1 ton of dry mass because the heat generation is done from the dry mass. And then we have to equalize this to the moisture content of the corn because it has 14.5% moisture. The result shows that if we store the grain at 30 degrees centigrade, that the respiration will consume about 70 tons of grain. That means a monetary loss of almost 17,550 Australian dollars. If we can cool that to 25 degrees centigrade already, we will halve the loss of grain, also in relation the monetary loss. And if we really can control the temperature to a very low level, then it means that we have almost no loss to fear. This can indicate or is indicating that grain cooling can preserve losses of grain by respiration. That's the first point where we can control the natural loss in a season where usually no cold air is available. That means just after the harvest, because we have to wait until the cold temperatures of the ambient will come by nature, which is in a different season. Until that time, we would lose grain in massive losses, and therefore the grain cooler can make you now preserving this grain from the respiration as we apply the cold air at a time when it's naturally not available. Let's change the topic and go really to a post-harvest problem. We see here the insects. These insects are the loss driver of post-harvest management. Almost 80% of the weevils, or 80% of the loss of grain is done by weevils. That means we have to look after them, and that's very clear for everybody who is storing grain, that he has to control the weevil. The nature of the weevil, as shown here, is that they multiply inside the grain, which is their natural habitat. They will make holes in the grain, they will lay their eggs and to start the next generation. But we also see on this chart that they produce a lot of fine material. And the fine material is our mass loss. The fine material is out of our hands. That means we cannot sell that anymore or process it. As we unload the grain, the fine materials will be separated from the grains. Another point, of course, which can create a concern is that we get some bacteria infestation. That means we become unhygienic, which is not so much concern, of course, for feed, as we sanitize it by the pelletizer, but for any human consumption, the weevil bacteria infestation would be a concern. Many of us do clean the grain before it goes to the silo. And we have here a similar situation given in this research, where a trial was doing a test on leather grain borer and infested intentionally with 100 adults one of these jars, where we have grain. After 7 days, the jar was emptied by the weevils, so that no alive weevil was there, and then this jar was stored under 30 degrees centigrade. What can be observed is that, of course, the weevils have been generating eggs, and those eggs are now hatching after 28 days, and the problem with the weevils starts to accumulate, to increase, that we see the grain itself is milled by the weevils, which is, of course, a tremendous mass loss. If we look now in the nature of the weevils, at this chart here where we have different weevils, each one presented in a column. Each column has a color code. The color code shows red, yellow, and white. The red is the area where the weevils do the most damage and develop very nicely. That means the most danger for us. And that is usually linked to a temperature scale between 20 to 35 degrees centigrade, where those weevils have best living condition. If we now would lower the temperature in the ambience of the weevil, then this activity of the weevil, the development will slow down. That is indicated by turning the color from red into yellow. We see that is directly linked to lowering the temperature, usually lower than 20 degrees centigrade at least. However, we see also that later the color from yellow changes into white. White indicates now the stage of hibernation. Hibernation means it's a stage when the weevils are not anymore acting. They fall on a hold mode, so they are, so said, switched off. They are still alive, they are not killed. Therefore, we would have to go on much lower temperature, but they don't harming us as they are not acting. That means they don't eat, they don't multiply, and they don't harm us. This can be achieved by using temperatures around below 20, below 20 for the lesser grain borer, but for others, grain weevils, we must go to 13 degrees, for example, which is definitely linked to grain cooling. And therefore, grain cooling can prevent the development and damages of insects by lowering the temperature. Here in the given example of a flour mill beetle, we see how that effect is working. The most advantageous temperature is here indicated by 28.2 degrees centigrade when the weevil multiplies, here shown at the population index 7.17, in 38 days of generation period. If we go lower now in the temperature, which means in the table we go up, then we see that with each lowering the temperature, the population index, which is the multiplication factor, is reducing. In the same way, the generation period is extending. So we have a double effect. We are not only preventing the multiplication, but we also increase the extension time until the next generation would come to life. This goes up to 18.17 degrees centigrade, where we see now the generation period is 85 days and the population index is 1. 1 means stagnating population. That means out of one weevil comes only one weevil alive. However, when we go to 18 degrees centigrade, for the given example, we hit the hibernation point. That means now no generation period does exist. That means they don't come to a generation exchange, and therefore the multiplication index, the population index, is 0. Here it's very clear that by grain cooling we can prevent any weevil activity. Coming to the conclusion, preventing weight and quality losses through insects, storage temperature over 21 degrees often must deal with ideal condition for the insects and therefore are dangerous. Below 18 down to 13 degrees centigrade, the hibernation of the weevil can prevent any harm to us, or I should say to the crop, and therefore no chemical treatment is necessary. No chemical treatment means no fumigation in the mean point, where fumigation is also a critical technology, not only because of its danger, but also of creating resistance insects if it's not applied properly, which is so said leading to higher escalating costs from season to season and to more danger for the applicant, for those who apply the grain, but also for cost driving up. In addition, residues may also be a concern for the future. However, grain cooling can prevent this. Now we make an excursion to unloading and loading of silos. We know that when we load a silo, we bring all the grain to the same level of height. However, when we load the silo, then we let the grain fall from that point down. We assume that our grain is uniform, but it isn't. It can vary, for example, here with the corn, plus minus 2% of moisture content. That means that when we let this grain fall down, it will behave differently. Moist crop, heavy crop will develop a higher energy in its moving down, which leads to their moving after it has dumped to the ground to a further distance than light crops. Light crops will fall down and stay on its place, but the heavy crops will further roll and jump to the silo wall where they will accumulate. That means we have now moist crop, heavy crop on the silo wall, while the light crop will all be in the center. And that is now a critical situation because the heavy crop has now usually also the warmest place on the silo wall, where sun radiation can even drive it to very high temperature, and therefore respiration will be higher due to the high moisture content, as well as fungus can grow easily there. If we are now going to unload this silo, we see that we have a segregation by flowability. Light materials in the center will create an unloading funnel, will come out first of the silo, but the crop which is more critical and more precious for us will stay longer, will stay in a dead zone which will not start moving until really the unloading funnel comes to that point. That means it stays longer and it gets more problems in agglomeration by water and dust or by fungus infestation. That is easy to observe if you look into a silo which has critical fungus infestation. Here shown in that picture. We see on the left side there is a silo wall where this infestation of fungus has come to a very extreme level. We see the white spots on the corn, but we see also that on the right side of this picture that the infestation level is much less. That means there are the dry kernels, which have no chance to be infested by fungus, while the moisture content is rather low. If we look into the fungus development shown in this chart here, we see that different fungi have their different living condition stated by temperature, relative humidity, and grain's moisture content. The color code will indicate what fungus is here shown, but we can already see that whenever a crop is more moist than 14%, higher in relative humidity to about 68%, and in a temperature range between 20 to 33 degrees centigrade or higher, then the fungus can grow easily and affect. Usually people state that my crop is dry, we need 14 or less. That is mainly true, but we also should consider that respiration activity can lead to higher moisture contents and the fungus will start directly acting. In addition, remember, the loading of grain will lead to a segregation by weight, and the heavy kernels will definitely be affected by the fungus in the end because they have a higher moisture content. When we now apply grain cooling, here indicated by the blue area, we see that we open a safety belt. In this area, no fungus can grow, and that means we can even store grain beyond 15, almost reaching 16% moisture content without getting any problem of the fungus because the temperature prevents its growth. That means grain cooling can prevent fungus development and, of course, the most critical point from there, mycotoxins. Usually mycotoxins have an effect to human consumption of food, but more critical even for animal feed, where this fungus on the mycotoxin must be prevented at any time due to the fact that otherwise it comes to economical loss by the feed. And that is something which cannot be tolerated, or it must be saved by using chemicals like fungus inhibitors or mycotoxin binders, which bring additional cost to the feed production. By grain cooling, we can definitely prevent this and make the grain safe. How the combination of grain moisture content and grain's temperature is leading to better storability of time is shown in this diagram. We see on the left side the grain's temperature coming from 4 to 32 degrees centigrade, and on the right we see a scale of grain's moisture content, which is going from 13 to 23. In the middle we have another scale stating days of good storage time. If we have now a crop of a certain moisture content, here indicated by 14%, and we store it at different temperatures, we can indicate how long a good storage time would be. The first example, the blue line, shows we have a grain 14% and stored at 29 degrees centigrade. And it is indicated that in about 30 days we'll have critical situation where the grain quality will be affected. If we can lower the temperature to 25 degrees, the good storage time extends to more than 64 days. But if we apply really hard grain cooling, then this will give us a good storage at 10 degrees centigrade for 1 year's period. That means for any critical crop, I can decide how long I can store if I use grain cooling to reduce its temperature. Another side effect which is very important to realize is that while we do grain cooling, we have a drying. The drying is due to the physics of air, as when we apply cold and dehydrated air, which will be warmed by the energy of the grain passing through the grain, then this air will increase its temperature, and at the same time it will reduce the relative humidity of this air. Thereby it will allow now to absorb moisture from the grain by the effect of the sorption isotherm. That means the hygroscopic behavior of the crop. However, the drying effect is limited. Here we see that if a grain is 16% and more, then the drying effect is limited to a little bit more than 1.5 up to 2%. If the grain is already dry, that drying effect is rather reduced. We see that from 14 to 16%, we can only reduce by half to 1.5% moisture. That's due to the fact that the energy content of the grain is limited and rather low, and we cannot work like a mechanical dryer where we can easily add more energy to have a more serious drying. However, this drying effect is for free. It goes along with the grain cooling and no further action. And now remember the talk we had about the segregation of weight, the moisture variation of grain. And now you realize that the grain cooler can homogenize the grain when applied, because more moist grain will lose more moisture when grain cooling is applied, while the dry crop will rather stay in the constant level. That is also shown by the investigation here on an example of grain's moisture homogenization, where we have on the left side a grain which was managed by grain cooling compared to on the right side a grain which was just mechanical dried. We see here in that diagram, which is indicating the percentage of grain which has a certain moisture content. On the left side, we see the moisture content variation is between 14.3 and 15%, leading up to percentages of 20% on 14.7. On the right side, we see that the grain varies in its moisture content wider from 13.8 to 15%. That means we have here a more inhomogeneous moisture content, which is of course critical when we apply this crop into our processing. We can also say that by grain cooling, we homogenize by the free drying effect of the grain cooling our grain, which will lead us to better processing efficiency. The combination of drying and cooling for moist crop, for example a paddy, which is usually always harvested in high moisture content, is shown here by that chart. And that will also apply to any other crop which is harvested very moist. We do first a mechanical grain cooling. Here for the paddy, of course, we have to apply some tempering in between to prevent head rise losses in the milling process. But after the last step of drying, we will apply a cooling. This cooling will now allow us to lower the moisture content even lower for free, so no drying cost. And then we stabilize the grain on a lower temperature, here on 15 degrees centigrade, for the continuous storing time to prevent respiration, beetle infestation, as well as fungus development. If a grain is already very dry, of course, drying is maybe not needed by the mechanical dryer, but grain cooling can still preserve the grain from getting spoiled. Now we are already rather at the end of this short presentation regarding grain cooling and grain preservation. And we can now collect all those advantages which we have mentioned during the presentation. We achieve a riskless long-term storage without quality loss. We can conserve the freshness of grain, particularly if it's a grain which is usually losing over the storage period at high temperatures. We can minimize the respiration losses. That means no mass loss will happen. We protect the grain from insects and their damages without doing any chemical treatment like fumigation. That gives us certain advantages where we can now also protect organic grain, which is usually not allowed to be fumigated at all. In addition, with the grain cooling, we protect the grain from fungi and their mycotoxins, which will avoid us in applying any fungus prevention or mycotoxin inhibitors, particularly in feed products. We can reduce drying costs because the free drying effect of the grain cooling comes along by lowering the temperature. However, we cannot over dry our grain, which is also not a concern in making weight losses for our trading or for our production. That means we can really stabilize the grain for the storage period by looking into the moisture content. A uniformity of moisture content has definitely advantages in certain industry where we process the grain, as it will allow us to have a more uniform application, which will increase the milling performance and also its efficiency. It is very clear by the one-time application of grain cooling during the harvest period, when we lead it into the storage, we have a simplification of the grain management. No need for aeration, no need for fumigation, no need for circulation of grain inside the silos to prevent heat rise or to prevent fungus, insects. It is just done in a one application. We can also not make us dependent on weather conditions, as the grain cooler will always run on the same settings and the same results, never mind what is outside happening. We also don't have the risk of moistening the grain by aeration, for example, as a grain cooler will never bring moist grain into the silo as long as the settings of the unit are chosen wisely. No breakage, no grinding of grain during grain circulation. If we circulate grain to dissipate the heat by elevators, then of course we do some grinding, which will lead us to either weight losses or even to quality losses when we look into the rice and paddy production. Another point is of course very clear, conservation of germination point. As we do apply cold air, the germination strength on the seed is remaining in high level as respiration cannot weaken the grain. Aside of that, as mentioned, fungus can also not damage our grain. So it's also useful for any seed storage. The most important point is that this grain cooling application is a money game. We want to increase the revenue. We do an investment to improve our market position, to make more cost saving or to prevent any losses by damages. And that's for the amortization period of a grain cooler is rather short. Usually in 1 to 2 to 3 years, the money returns by those cost savings, by those quality improvements, by those mass conservation of grain, so that we have more to and better to sell, or we have crops to sell in a no time when it's in the market not anymore available with outstanding quality. Those gives us economic benefits, which definitely will give us the money back for this investment in a very short period. Now I have to thank you for your attention. Was a pleasure to present this here in the webinar. And I would appreciate if you now come up with your questions or with your comments so that we can further go along in our discussion. Thank you very much.